All right, so in the last video, we spent some time evaluating limits using graphs or the graphical approach. In this case, we're going to use, or in this example, we're going to use the numerical approach that we talked about at the end of that video. So what I want to do is evaluate this limit right here. It's the limit as x approaches 5 of x squared minus 25 over x minus 5. Notice that I'm not writing an f of x here anymore. I'm giving an actual algebraic representation for our function. And more often than not, this is actually how we're going to see these limits. The reason I was using f of x before is because we were given graphs, but we didn't want to imply that there was any more known information about those functions. So we kept it a little bit vague by just writing f of x here. Now, though, we know exactly what function we're looking at. So how do we go about evaluating this limit? Well, like we said before, when you're evaluating limits, you're not necessarily saying what that function is equal to exactly at the number here. So we're not plugging 5 directly into this function. In fact, you would see that if you tried to do that, the function is undefined there anyways, because if you plug a 5 in, here in my denominator, I'm going to get 5 minus 5, which is 0, which regardless of what you get up here, you would be dividing by 0, and that you can't do. So instead, we're plugging in numbers that are just very, very close to 5, but approaching from either direction. So in this column of the table that I've created here, we're going to be approaching 5 using numbers that are smaller than 5. That would mean that we're approaching from the left. And what I want to do is try a few numbers, but have those numbers continually get closer and closer to 5 as I move down this column. So 4.9 is very close to 5 while still being less than 5. So that would work if we're approaching from the left. Now, what I would do is I would take that 4.9 and plug it directly into this function. So I would do 4.9 squared minus 25 all divided by 4.9 minus 5, like this. I'm not asking you to do that by hand, because if you think about how many different values we're going to be plugging in, that's kind of a monster to have to do all of that by hand. This is where you use a calculator. So if you have a graphing calculator, it's easy to punch these in. If you have a scientific calculator, it takes a little bit more like step-by-step plugging things in using that type of a calculator, but you can do this on either. If you were to do that, plugging 4.9 in for the x's here and evaluating this, you're going to get 9.9 as an answer. Okay. Now, if you were to do the same thing, but this time plug 4.99 into this function. So now we're using a number that's still less than 5 because we're approaching from the left, but it is closer to 5 than the previous one was. So we're approaching 5 as we move down. If you plug this into that function, I'm not going to rewrite this with an extra 9 in it. I'm just going to tell you what it comes out to. You get 9.99. So I get a number that's different from this one, but it's not super different. It's pretty close. What if I plug 4.999 in? Use a calculator, verify that this is what happens, but we would end up with 9.999. And then, as you might have guessed, if I plug in 4.9999, I'm going to get 9.9999. So this you should verify on your own with a calculator that these are coming out correct. But the point of doing this is we're supposed to look at this and think, well, what do these numbers appear to be approaching? They all have a 9 in the ones place, and then they have decimal values it looks like just this ever-growing string of 9s. This is getting very, very close to the number 10. Every time I put another 9 or any non-zero digit after this, for that matter, this number is getting closer and closer to 10. So it looks like this limit might be 10, but we haven't checked what happens as we approach from the right. So we have to do that also. So let's plug a 5.1 into this function and see what happens. Go to your calculator, plug a 5.1 in for here, so that you get 5.1 squared minus 25 divided by 5.1 minus 5. See what your calculator gives you. It should give you 10.1. And then if you plug 5.01 in and do the same thing in a calculator, you get 10.01. And if I plug 5.001 in, I end up with 10.001. Similar here, if I plug a 5.0001 in, I get 10.0001. Okay? And like I said before, try this. Plug this into your calculator and see if you're getting the same thing. If you're not, then that actually means that you're probably punching the keys in the wrong order or something's going wrong. So it's a good check to make sure you know how to use your calculator. Is this approaching 10 as I go down this column? It does look like it, doesn't it? So 10.1 is pretty close to 10, but a little bigger. 10.01 is smaller than this number, but still a little bit bigger than 10. That would mean it's closer to 10 than the previous one. This is even closer to 10, and this is even closer to 10. So regardless of which direction I'm approaching or which column I'm looking at, both of these appear to be approaching 10. So my guess is that this limit is 10. Now, as with the graphical approach, you'll notice here that we're still using the term estimate. I'm still calling this an estimation for my limit because even though it seems pretty clear that we're approaching 10 in either direction, what if we're actually not? What if this is going to keep going until we get to 9.9999 where there's like 100 nines after that decimal point and then it stops growing? And then what if this actually shrinks down below 10 and also goes towards that 9.99999 with 100 nines in it? We don't know just from this type of an approach if that's going to happen or not. We're making an educated guess that says that this looks like it's approaching 10. So starting in section 1.2, we'll come up with a method where we don't have to estimate these anymore. But this is kind of a starting point for us. Okay, so I'm going to say that this limit is approximately 10. Let's try another example. This time I want to look at one-sided limits. So for a one-sided limit, if we're going to use the numerical approach, we can still use a table, but we only need to use one of these columns because we're only approaching from one direction instead of two simultaneously. So let's take a look at this function. Now this might look like a scary function because it's so complex, but these types of functions arise a lot in application. It's what we call a piecewise function. And you should have seen these before in a previous class, but if it's been a while or if you don't remember ever seeing these before, when you have this form for a function, f of x equals this big curly bracket, and then you have some different expressions in here followed by commas, and then after those commas you have these inequalities involving the x. The way we interpret this is that the function f of x, we use different expressions to evaluate it depending on what interval x lives in. So let's say I wanted to evaluate f of -10. I don't plug -10 into all of these. I come over here and I say which inequality includes -10. So if I plug a -10 in for the x here, -10 is less than -3. That's true. -10 is not a part of this interval. It's not a part of that one. So -10 being less than -3 means that when I want to plug a -10 into this function, I use this expression instead of either of these. Okay? That's how we use piecewise functions. We first decide where does my input live. Once I've made that determination, we are able to choose which of these expressions we're using. So coming down here, I want to evaluate a couple of one-sided limits. First, I want to take the limit as x approaches -3 from the left of f of x. So where is -3? I see -3 showing up in a couple of different places in my piecewise function here. But the fact that I'm approaching from the left means I'm using x values that are less than -3. And I'm looking at this, I'm saying I copied the wrong inputs in my table here, so I'm going to have to fix that real quick. Okay, my mistake. So let's fix these. So -3 is what I'm approaching, but I'm approaching it from the left, which means I need to use numbers that are smaller than -3. Here's some numbers that are smaller than -3. So -3.1, -3.01, -3.001. I have to cram it in here now. -3.0001. Okay, so I'm going to plug those in to a calculator, and figure out what those are equal to. Since I put the wrong numbers in here, I'm going to have to go back and redo that, but that's okay. I can do that in a moment. Let's come over to this one so I can return to this one in a moment. In this case, we're approaching 0 from the positive direction. So if I look at f of x, where is 0? I see 0 appearing in a couple of different intervals here. And let's see, if I were to approach 0 from the right, I want to use numbers that are slightly larger than 0. So I'm using these x values here. All of these x values being greater than 0 tell me that I'm looking at this interval right here. This is the only place where x can be greater than 0. So that means I'm using my natural log function. Okay, so specifically natural log of x plus 1. I would start by plugging 0.1 in for that x right there, which would give me natural log of 1.1 when I do the addition. Use a calculator for that. That's not something that you're meant to do by hand. It's not going to happen. Okay, so let's see. If I were to plug that into a calculator, I'm going to see 0.09531. And then if I do the same thing, but this time plug a 0.01 in, again, I've done this in advance, so I know what my calculator is going to tell me. It's going to tell me that I get 0.00995. Then if I plug in a 0.001, my calculator would give me 0.0009995. And then if I plug in this 0.0001, I'm going to get this long decimal, but it looks kind of similar. I'm going to have 4 zeros after my decimal point, followed by 4 nines, followed by a 5. And all of these are truncated, so there's more decimals that come after that, but I just cut it off there. All right, looking at this, what do you suppose the limit is approaching? Or what do you think our function is approaching as x approaches 0 from the right? Well, let's think about it for a second. 0.0 is a small number in the sense that it's close to 0. 0.00995 is even closer to 0. I have a couple of zeros after my decimal point, so this is a very, very small number. This number is even smaller, and this one is even smaller. It looks like these are approaching 0, especially since I keep getting more and more zeros after my decimal point. My gut tells me that this is approaching 0, so I'm going to use that as my answer. Okay, now returning to this problem right here, I need to plug these numbers into my function, and because all of these numbers are less than -3, I'm looking here. That's where my piecewise function is directing me. So I'm going to be plugging them into this expression right here, x cubed plus 27 over x plus 3. Now, I had done that ahead of time, but I had done it with the wrong numbers because I put some wrong numbers in here. So I'm going to turn to my computer here. I know you can't see it. And I'm going to enter these values, these new values in, so I can give you some correct outputs. So you can't see what I'm doing here, but I'm plugging some numbers in over x plus 3, right? Okay. All right, so starting with our first value, if I were to plug -3.1 into that function there, what I end up with is 27.91. That's what my calculator is giving me, 27.91. Okay, and now what I want to do is plug in some of these other values. So if I plug in -3.01, I get 27.0901. That's what my calculator is showing me. Okay. You might even be seeing where this is most likely going by this point, but we don't know for sure yet, so we want to make sure we're approaching this correctly. Let's plug in another 0. So if I do -3.001, plug that into my function, I get 27.2 zeros, a 9, and then 2 zeros and a 1. And then let's try one more. If I do -3.0001, just did that in my calculator. Let's see if I can squeeze this in there. I get 27 point, and then I get 3 zeros, 1, 2, 3, a 9, and then 3 zeros and a 1. 1, 2, 3, 1. Okay. So what I'm seeing here is that these numbers are getting smaller because I keep getting more and more zeros after the decimal point. But I always have this 27 here for the whole numbers place, like where to the left of my decimal point. So this side appears to be going to just a long string of zeros. And 27 with nothing but zeros after that decimal point is just the number 27. So my gut tells me that this limit is going to 27. Okay? I'm going to get a little creative there because I had to do a little bit of calculating that I thought I had done in advance, and I did not. That's okay. All right, let's go ahead and move on to, excuse me, the next topic in this section, which is what we call infinite limits. So we've already seen that limits can fail to exist. And usually, the types that we've seen that happen with are when a function is approaching one number from the left, but a different number from the right. We've already seen that happen. There are other ways that limits can fail to exist, however. And one of them is if a function, as you approach x, either from the left or from the right, if that function is just getting larger and larger and larger and not appearing to taper off anywhere, or if it's getting smaller and smaller and smaller in the sense of going towards like negative numbers, past 0 into the negatives, negative 100, negative a billion, negative a trillion, it keeps going negative more and more into the negative direction. In those cases, it doesn't appear that the function is approaching something finite. It's just exploding with growth either towards what we would call positive infinity or negative infinity. And so we use infinity and negative infinity to notate how those limits are failing to exist. So here, if f of x becomes arbitrarily large as x approaches a from the left, then we write this. The limit as x approaches a from the left of f of x is equal to infinity. Similarly, if f of x becomes arbitrarily small, meaning in the negative direction, as x approaches a from the left, then we write this. The limit as x approaches a from the left of f of x is equal to negative infinity. A couple of things I want to make a note about here. First of all, the term arbitrarily sometimes gets people thrown off. When we use that term in this context, what we're meaning is that we can make f of x as large as we want to make it by simply taking numbers that are close enough to a, in this case from the left. So I can do this in reverse. I can pick as big of a number as I want, say a trillion. This would tell me that there is a number just to the left of a that I can plug into this function that gives me that trillion. And I can get bigger than that as well. Similarly down here. We use similar notation if we're using limits that approach from the right or if it's a two-sided limit. So this minus here might be a plus in one of those cases, or it might not be there at all in the case of a two-sided limit. The other thing that I want to point out that's really important, and it may not be that crucial in a business calculus class, it's a little bit more important in kind of a pure math context, but this notation can be very, very misleading. And the reason why is because it appears to be saying that the limit in here or here does in fact exist, because I'm saying that this limit is equal to something. But in fact, this symbol for infinity or this symbol for negative infinity, these are not numbers. Infinity is not a real number. And so when limits exist, they're always equal to a real number. By writing this notation, what I'm saying is that the limit as x approaches a from the left of f of x does not exist, and here is how it is failing to exist. I'm describing its behavior that's leading to the fact that this limit does not exist. Okay, so it's a little bit more specific than just writing d and e for a limit that doesn't exist. That's kind of what I'm elaborating on in this paragraph. So let's jump to an example. I want to use this graph right here to evaluate a few of these limits that I have down below. Let's start with the limit as x approaches negative 3 of f of x. So for this one, as x approaches negative 3, what I'm doing is I'm looking to the graph because we're using the graphical approach for this one. If I approach negative 3, I think I said from the left, but I don't actually have a negative up there. So we're just approaching negative 3 either from the left or from the right. So if I approach from the left first, I'm using numbers that are coming from over here on my x-axis, and that would mean that I'm approaching -3 along the curve this way. But look at what happens to it. The curve just goes off the page. It's going up, 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 and it doesn't appear to be slowing down at any point. If I approach -3 from the left, I get the same behavior. I see that my function is just skyrocketing off the window of my graph here, and it doesn't appear to be tapering off there either. So what this does is it creates what's called a vertical asymptote, which is something you should have learned about in an algebra class. And those vertical asymptotes are exactly where we get this type of thing happening. Okay, in this case, both of these sides of my curve are approaching positive infinity because they're getting larger as opposed to smaller. So I would say this limit equals infinity. And again, remember, I'm not actually saying that the limit is equal to a number called infinity. What I'm actually saying is that this limit does not exist, but the way that it's failing to exist is that it's getting arbitrarily large as x approaches -3. Check this one next. So the limit as x approaches 2, but this time just from the right. So here I'm going to find 2 on my x-axis, and we're approaching from the right, which means the curve that I'm going to be using for that approach is this one here, not this one here. So I'm approaching from the right, and as I get closer and closer to 2, I am also seeing that this curve is going towards infinity. Okay, so in this case as well, our one-sided limit is also infinity. Okay, what about if I approach 2, the same number, but this time from the left? So this time I'd be using this part of the curve because those x values are smaller than 2 and they're approaching 2 from this direction. If we approach from the left, this function appears to also have a vertical asymptote here because it's getting steeper and steeper and steeper and doesn't appear to be slowing down, but it's going down instead of up. That means that we're going towards negative infinity. This function is getting arbitrarily small as we approach 2 from the left. Last example. If x is approaching -1, what is the limit as x approaches -1 of f of x? Well, in this case, it's not a one-sided limit because there's no minus or plus up there. It's the two-sided limit. -1 would be here. It's not labeled, but from the scale of my graph, I can figure out that that's where -1 would be. And whether I approach from the left or from the right, in both cases, our curve appears to be approaching this vertical asymptote, and they're both going down. So that would imply that this limit fails to exist and it's approaching negative infinity. Okay? We can do these infinite limits with the numerical approach as well. And this will be the last example that we do for this section. So let's try a couple of limits that turn out to be infinite limits and see what that looks like when we take the numerical approach. So first of all, I want to find the limit as x approaches 7 from the left of x plus 3 over x minus 7. And then I want to do the same thing, except this time approaching from the right. So if I'm approaching from the left, I'm going to use these numbers that are just slightly smaller than 7. But getting closer and closer to 7 as I go down this column. So if I were to plug in 6.9, you would use a calculator to do that. You can go and plug that in and see what happens. You end up with -99, okay? If you plug a 6.99 into this expression, you get -999. If you plug 6.999 in, you get -9,999. And then if I plug 6.9999 in, I get -99,999. A very clear pattern that's appearing there. And if that pattern continued, this would not be approaching anything finite. Each step that I go down in this column, the number appears to be getting larger by another factor of 10 pretty much. So it's getting very, sorry, I said larger. I should be saying smaller because these are all negative. So this is getting more and more negative. It's getting smaller and smaller, and it doesn't appear to be leveling off in any way. So I would think that this limit is equal to negative infinity. So for part A, I would say that the limit as x approaches 7 from the left of x plus 3 over x minus 7 is equal to negative infinity. Okay, that would be my answer to that one. Similarly here, I'm going to do the same thing, but I'm going to approach 7 from the right. So I'm going to plug in numbers that are slightly larger than 7, but getting closer and closer to 7 as I work my way down. 7.1 is where I'm going to start. If I plug a 7.1 into this, again, you verify this in a calculator, you should get 101. If I plug in 7.01, I should get 1001. And then here, plugging that in, I'm going to get 10,001, and plugging that in, I'll get 100,001. Again, strongly encourage you to go try this in a calculator. It's good practice, okay? Similar to what's happening in this column, I don't appear to be approaching anything. The numbers appear to be getting larger and larger and larger, also by like an entire factor of 10 pretty much every time. I don't see this leveling off at any point. So this appears to be going towards positive infinity because these numbers are positive and getting larger and larger. I would then say that the limit as x approaches 7 from the right of x plus 3 over x minus 7 is equal to positive infinity. Okay? All right, so that's going to be it for section 1.1. And starting in section 1.2, we're going to look at other approaches to solving limits.